brings it a little bit closer to reality. So we got far less approximation. But still, those approximations are present in different modeling approaches. So we briefly mentioned that yesterday when we talked about the difference between 2D and 3D. Reality, the way we experience space, is three-dimensional. But we are saying in some situations, depending on loading, depending on geometry, we can ignore third direction, or we can predict behavior in third direction, so we don't need to model third direction. Yeah? Now, I'll touch a little bit on that story that we talked about yesterday. So, if we are modeling something like this, yeah? And that block is got thickness. Now, if you are to use, I don't know how many elements are going to be here. If you use the 12 elements there to measure the front face. Now, if you are to capture what happens through thickness, you should at least have 3 elements through thickness. 1, 2, 3, in that direction. Which immediately, if you got a thickness to worry about, complicates things. What I mean by complicated is adds more nodes, more elements, more calculations. So all of a sudden from 12 elements, we got 12 in that block, 12 in that, 12 in that. So 36. So at least your model will be 3 times more expensive. It will take you 3 times more time to complete and everything else. So obviously you can see motivation why we are trying to avoid 3D modeling as much as we can. So what we can say is that, okay, that stuff here, we can model as a 2D if we assume certain things. And then we develop those 2 assumptions. First assumption is that we have plane stress. The second one is that we have plane strain. Now, what does that mean? Well, plane is plane. Yeah? It means that all those stress or strain live in a single plane. There's nothing happening in third direction. So plane stress means that stress in z direction is equal to 0, and plane strain means that strain in z direction is equal to 0. That is the assumption, and that is the model. Now, remember what your job is. You said, here's the reality, and we have to find best model to match that reality. Yeah? And then we got models. We got truss being simplest, then we got beam, then we got 2D plane stress, 2D plane strain, 3D shell, and 3D solid, for example. So, whatever that reality is, you have to find best and cheapest model for it. Yeah? So, if your reality cannot be captured by plane stress and plane strain, that means you cannot use them. I mean, you can, but your results will be wrong. Yeah? So that's the whole point of this course, is sort of understand what are the limitations of each? So remember we talked about trusses and we said they don't bend. So they are structural elements that don't bend. So if we have a structure in which we don't have bending, we can use truss elements to model and be of good accuracy. If we can't, then we have to move to the next level, and so on. This one here, 3D solid, as I said, being most expensive, but generally can be used for any problem. Now, if you've got a simple cantilever structure like this, you can use all of those maybe to model. But cheapest one would be which one? Beam. Yeah? Any quickest and cheapest. So when I say cheap, in a sense, how many nodes it takes to model that. You already, some of you experienced limitations of the license. Sometimes when in your company or where you're working for, they may say, look, we can only afford, 2,000 nodes. You have to live with it. So that's limitation, that's resource. Your computers could be slow. For complex assemblies, complex structures that we have several million nodes, it makes huge difference if you're going to get results tomorrow or next week, because everything else then gets delayed. So that's why we have those approximations. Now, what makes structure plane stress? As I said, if we got all stresses living in this plane, how do we assess that? So we have to check whether all the loading is in plane, and also the thickness that we have is quite small relative to other bits. So structures that may look like this. This is typical example of plane stress problem. So you can assume that by taking this load, this face, that in modeling only this front face, it's basically a slice that repeats through thickness. So you'll have another slice, another slice, another slice, another slice, all the way to the end of the back, to the back face. So it's a repetition of that front face. What it means that that load there is essentially applied across the thickness like that. So when you do your plane stress or plane strain model, and you got a force apply like that, it means that what you're modeling there is a front face that repeats till the end of your thickness. So it means that force is essentially repeating like that. So it sits on that edge. Yeah. What is the typical example of plane strain? Plane strain means there's no change in length, in thickness. Or if there is, it's only small. So it's usually something that is really long in Z direction. So, for example, if you are modeling rail track, so it looks like something like this. It's quite long, yeah? So that's front of it, yeah? You will model that, and if you got a load, because of the length of it, there will be only small changes in length. Remember what strain is. Strain is change in length over original length. And if you got a small length of change length of 0.01 compared to, 1,000, strain is quite small. So we can say it's almost 0. So that would be a good example of plane strain problem. Yeah? So what you need to understand is, given reality, whether we have a case of plane stress or plane strain, and then we can decide whether one of those is true. Often we may have plane stress and plane strain happening at the same time. So either of those will work. Yeah? Does this make sense? Yeah? Okay. So let's now look at this exercise, the first one. This one here. How would you? What do you reckon? What would this be? Plane stress or plane strain?
Plane stress.
Plane stress. Yeah. If we had this load applied like this, rather than like that, applied like that, would it be? Could we model this as a 2D?
Shell.
We couldn't. So it will be 3D, it will be 3D shell. Why would it be 3D shell? Because thickness of it is much smaller compared to other 2 dimensions. Therefore, it's a good candidate for shell. Yeah? So, this example, already we solved it, is plane stress. So we can model this using 2D solid. Yeah? In your exam, you'll be given something like this. You'll be given a problem, and then you have to recognize whether it's plane stress or whether it's plane strain. Yeah? You also need to recognize what sort of boundary conditions would you model. Yeah? Okay, so let's do this. Let's model and then learn a few things about 2D solid modeling.
没有，我在讲那个是什么 ？I think it's a 3D shell。没有，我忘记这个怎么扫。看一下我的之前。故意没有。
你的手机放多少？
我放1000。
距离呢？
没搞好呀，那个 分区是，如果你有一个很长的东西，把它的 shape 是 all the way 一样的， then 你就要用分区。你 just 想一下，只要它的那个 thickness 没有 ，in a way 你可以想 ，maybe 如果它的整个它的 sectional 的那个 area 没有比 ，OK 它 sectional area 如果它的 length 比它 sectional area 大很多 maybe like 5倍以上 ，example 5倍以上，你 just 当做是分区。如果它是 maybe 在它的 section maybe 大来 maybe 1.2到2 times 到4 times 5 times 都算是分区。
Good question. That's what I was about to say. I was about to open my mouth and say it. First thing that you need to do is obviously define units. Decide is it going to be newtons, meters, millimeters, pascals, megapascals. So once you got that sorted out, then you start thinking, okay, out of these potentially 3 components, what I'm interested in, do I need to model that back face or back plate?
No.
Do I need to model bolts? Or I'm going to be just good with the plate that is there? Yeah? And it's the first thing that you need to make decision on. Yeah. So plate is attached to this back plate through 4 bolts. Do you model everything? Question, well, the answer is not that simple. The answer is not, this or that. It all depends on what you are after. Yeah? If you are interested in stresses in a plate, and what happens when it's going to be strong enough, this and that, detail about bolts may not be important. So you can ignore it. You can replace bolts with the boundary conditions. But if you're interested in sizing bolts and seeing how strong those bolts are, you would need to model those. If you are interested in what's going to happen to the back plate, you would need to model. So it depends, again, with the FEA, you have to understand it is quite situational. In a sense, you have to understand what is the situation and what are you after. What are you after in this particular problem?
Maybe which one? The whole 0.1, 0.13, 0.23. Well, that one is the whole distance, but the whole itself is 80
It gives you, probably instructions what not to do, but the idea is to figure out, given this load, how much of reaction force would be there, so we can go and choose bolts. Yeah. So whether it's going to be M5, M8, M12, M24, or whatever. Yeah? And that's basically what this exercise is about. Figuring out how much of reaction force we have. Yeah?
ATM 所以你要放，那通常是一个就说要放哪里？你不可以这样毛掉，因为它一开始毛的，它会毛到那个 solidity，所以你换了这个 它不会有一个洞，你一定要画那个背线，然后你把
So
那个洞挖。
where's the design aspect here? Obviously, like you can see with all these, we have to do a couple of iterations. So what is that design aspect in this problem?
The size of the hole.
Size of the hole, correct. The assumption is if the hole is bigger, we can have a bigger bolt. Yeah. So, for example, if we assume, let's say M4, so diameter is 4 millimeters. You go through calculations and you find out that per bolt you have, I don't know, 150 newtons. Then you go into catalog and see how much M4 of particular strength can carry. And if it's less than 150, then we have a problem. We have to go with the bolts higher, with the bigger bolt. Yeah?
set 这些，你要按 OK，你做好这个传一个，你要按 OK，你要把这个传一个 generate 出来。OK 了，你传一个，按好，把那个传一个那个出来，直接用这个第三个，你按，等你再放那个什么，哎，只可以留10个，剩下的线全部丢掉。把它的舌根每次都是有一个，所以你要换成一个。那就不对啊，我应该，still，no，不 still。extrude，它有 extrude，you have to extrude the triangle first。extrude， we don't need to extrude actually. Oh, you mean the thickness is it?
This is the middle of the, this is the middle of the triangle.
Middle.
Extrude is the thin, right? Extrude is thickness.
Yeah.
Because it's a
You
bit
do
stress.
3D drawing, or
Yeah, 3D.
you're supposed to do 2D.
Really.
Yeah, you need to do 2D.
Then the thickness ah.
Thickness is 6. 6 mm.
This is all the cross section.
Yeah, under the cross section you need to see.
Oh.
那你去 set 那个冲微电出来吗？
2 mm.
而且你要怎样去 define 那个 dimension 的 units？从微电的那个，
不是 radius 是 radius。
哦，那 radius 啊，
Yeah, radius 你 just 放 9 divided by 2 18 divided by 2
哦，是 radius。
Sharp.
Yeah. Something I can't remember.
shot come on it. My shot it. Complete land.
Which one?
My shot. This one shot.
This is what?
This
Yeah.
one shot. 3D. 3D.
No, you okay? So now right, you need to input the load right. You won't have any load there, so you need to put a partition, which is the no. Like, here is correct. You go to the last, the middle. You go to the middle. Up one more. Yeah, you press this one. Then press on the face. Yeah. Okay. So now you can draw. So you just draw the distance where the load is. Just draw a line across. I don't know how to do these partitions.要，你没有关掉。
Shell. Sections under shell and
This one should
homogeneous.
be solid, I think. The material should be set also.
Let's read. I think 6.
is a quick video about how to get.
Oops, sorry.
你是这样子，我应该做那个
没有没有，这个是这是 YouTube。
哦，
那种4,000 Cost is 4,000.
刀的
4,000 kilometer.对啊，2D 玩2D plane 嘛，是用 2D plane。
我做出来，不错，他做出力了。
Okay, so first thing, I mean, probably just repeating what you already know, but based on some questions that I had. When it comes to creating the parts in Abacus, there are different ways Abacus creates that material, and that is defined here. So first we are defining what sort of modeling space we are dealing with. Is it 3D space or 2D space? It's going to be 3D space. That means all above, so truss beams, 2D solid, they can be modeled in that space. So nothing exists in third direction. 3D, obviously, like, you know, we can have 3D beams, we can have 3D space, but it's important to understand that truss, as like a spring, it's one-dimensional object. It means it can only change or deform in one dimension. But that one-dimensional space object can live in 2D or 3D space. So this that can only go left and right can live in a space. So it can go like this, left and right. It can go up and down. You know, and this in both cases it can only go longer and shorter, but lives in 2D space. This also could live in 3D space. So it could be like that, but it's always in local sense can only go longer or shorter. So you could have three-dimensional beams if it's required. And an example of that would be if you have structure that looks like that, and you've got a force that goes on the side. Yeah? So maybe when you're modeling, you know, the traffic light poles, yeah? And you've got a wind load that pushes on a traffic light. So when you got there's traffic light sort of stuff, yeah? And your wind goes like that into screen, pushes against that. You know, this then needs to be 3D 3D beam structure. Yeah? So, then, you know, whether it's deformable or not, and at the bottom we've got a base feature. So again, this is called a base feature in a sense. What are we sketching? What are we creating? We've got a name shell. And don't get that confused with the shell and everything else that we are dealing. This is sort of modeling feature in Abacus. You know, they probably should have called it something else. But this is, and the difference is what is shown here. If I picked wire and did square, you will get this. So basically, you will capture lines that you're sketching. But if I do exactly the same thing, but pick shell, it means I'm capturing material that is enclosed by that square. So this one on the right, we can use to do the truss through the beam or something like that. But one on the left is one that we're dealing with the continuum element, the space, continuum material, rather than structural components. Yeah. So That is the difference between the two. So let's delete this and sketch properly what we have here. So it's shell, formable 3D, yeah. And so it's 600 by 600, yeah.
Pop up for what?
When you create a boundary section, right, this to determine x and y, right?
Yeah.
I cannot find it. It won't pop on my screen.
You close. Then you press the manager. The second one. The one bottom, yeah, down, one more up. Yeah, press this one.
See? 出来，
Yeah, why not?
这个好，
嗯
这来。
Oh, you use web browser?
Here don't have.
Oh yeah, correct.
你这我说你出来了，
Oh, that's true.
可以站个死，
Oh, that's it.
不知道死卡。这个你 just click continue。你再要回。
Set the boundary condition. You help me press control. Press and hold control.
Okay, now we can propose dimensions. So let's say what are we going to do?
Yeah.
So they'll be too big. So maybe we go for 12. Yeah. Oh, that's too small. So let's go maybe 10. Yeah, let's try. See what happens.
Yeah, oh my god.
Shit, man. They already gave you a school shit.
But I don't know how to make the mesh part because they say if you want a good mesh, right, it's supposed to be all square.
Partition.
But I don't know, whenever there's circle, I don't know how to make it nice.
Okay. That's what I have. Now, material, same story what we had before. We can maybe start with aluminium. Yeah, does it say like what material? Steel. Ah, sorry, there's already, it tells you the 18 millimeter, okay.
Yeah.
So we go that and it's steel. Okay, so we'll come back and we fix it. So let's go for steel. Okay, now, when you go with this section, it is a solid, although it's two-dimensional, but it's still solid. Homogeneous means it's got the same properties in all directions. So in X direction, Y direction, so on. What do you think, what material may not have same properties in all directions?
Composites. Composites.
Composites, yeah, depending on the fiber. timber as well, depending on the grain and so on. So you'll use different modeling approach. Yeah, so it's a solid, and here we've got this. So for all solids, it's the same prompt box. Now, this becomes relevant to you if you are dealing with the plane stress and plane strain. This is where you are specifying thickness. If you do not specify thickness, Abacus assumes default value. Default value is 1 unit, whatever that is, 1 meter or 1 millimeter. So here we put value in, and we say 6 millimeters. So for me, it's a number 6 because I'm using millimeters and units. Okay, now we go and assign that to our plate, and we are done. Now we go to assembly. You bring it in. Okay. Now, we can go and create a step. Again, it's linear perturbation. When it comes to loads, we can do easy ones, so which is boundary conditions, so BC.
boundary condition.
And it's fully fixed.
So I can understand the section. The option is not
For
When you click on new material section.
after the
Okay, load. Now we have a point of discussion. And this is something covered in last module. So, when we are applying point load, had it been a beam or a truss structure that looks like this, we got a nodes that are there, and with the structural elements, if you put a load at the node, it gets translated or transferred to the rest of the structure without issues. What we have here, this is not structural element or structural modeling approach. It's continuum. It means that everywhere inside here, we've got material, yeah? So, if we are to attach a force, we have to make sure to recognize what that force represents. Point load, does that exist in reality?
No.
No. So we are approximating reality. Now, approximation of that reality has got consequences. So everything that we simplify there are consequences. Our job as FEA engineers who runs these models is to understand what are the consequences of those approximations. Yeah? And whether that approximation is good and suitable. Yeah? So you could attach that force there to a point sum. What will happen and result as a result of that approach?
Localized.
We'll have highly localized stresses happening, and this bit here would probably deform and fail before anything else. Load may not be properly translated or translated to the rest of the structure. But we like those point loads or point forces very much because they're very easy to do. Just being put in there, done. So it saves us a lot of time. So choice, you have to decide whether you will use that or not. What would be alternatives to this? What would be alternative approach rather than using point load? Something that's more realistic. Pressure, yeah. So if we apply load on a bigger region, yeah. So if we, let's say, use that patch and apply pressure, that will be more realistic. Even if I use my finger to load something, still applies over a bigger area. It's not infinite. It's not a needle essentially. Yeah. Even needle has got some cross-sectional area. This is virtual. This doesn't exist in reality. So a better approach would be to spread that over a bigger area. How big? It's something for you sort of to make assessment. Yeah? But one way, and I would recommend that, is to make sure that we have a big area and then you apply pressure over that area, which will match up with that 4 kilonewtons. Yeah? Alternative to that would be to apply something called distributed load. I think you face this in solids 3 when you had structure that looks maybe like that. Sorry, probably guys that can't see it. And you got, it gets sort of represented like this. And tells you 3 newtons per millimeter. That is distributed load. You could apply something like that there, which is more realistic. But again, you have to figure out what values. So if you are to apply total of 4 kilonewtons and you got a width of half of unit meter, let's say, what would be your distributed load then? So you have to recalculate that. Yeah? Okay, so how are we going to deal with that? Any preferences? When you go and explore load, so we've got a concentrated force, we've got pressure, we've got a line load. These other bits are not relevant. So we can let's say let's explore this, yeah? Let's go with the concentrated force, yeah? And then we got a problem. Because what we need to do when we're applying force, there must be a node at location where we want to do. So how to go about this? Partition, yeah? So do we have where? what is that? It's a 30,
45.
45.5. So was that 5 or 6? So let's partition line, yeah? Partition line. Yeah. Center parameter. Yeah, so we got H, already partition, so let's delete it. So, what is it? It's 5 out of 6, yeah? Alright. 833.
It's 550.
I mean,
0.55.
0.55.
Yeah.
So it's 550.
550 mm.
And so, entire length is 0.6.
Yeah, total length, okay.
Yeah, total length is, so total length is 6, and we want this to be at 5, yeah? So what we got here is the parameter that says on here is 0, here is 1. Where should I be? Yeah? So it's a 5/6. Does that make sense? 0.833. So 5/6.
Isn't it 55 or 60? So it's 11, 12, not 5 or 6. It can be 0.8.
What are they saying? Say again.
0.55 or 60. It's not 5 or 6.
0.55. Yeah. Right. Let me change this. Okay. So what did you do the calculations?
0.91666.
91666.
91666.
9166. Okay. So load, we got it sorted out. There's a point there. Then we put concentrated force. Continue. And we got 4,000 there and 0 in Y. Okay. Now, trouble. So, if you go and click on this button here, it says mesh controls. Through that, we can control shape or preferred shape of the elements, as well as how they are attached to our geometry. Yeah? So we may say, okay, let me go for quad, so all of them to be four-sided, and any orientation is okay, it doesn't need to be structured. And then if you go and seed it, we got that, which is not good. Why is not good?
Not structured.
But it's not structured, okay, but it's not always possible to have structure. But what's wrong with this mesh? Why we are not happy with this?
The area of mesh not equal in area.
But does it have to be?
Not really, but it's best to be.
Point of interest is
Yeah, so we got two comments. So we got point of interest there. We also saying that, that not all elements are the same. That's sort of a bad side, yeah? What else? What else is not that good about this? Or what else we can change? Where's our area of interest? Here. So this bit here, that space, or more precisely, probably those. That is the reason of interest. That is the place of interest. So you would expect to have at least in those regions finer mesh. Yeah? Everywhere else is not an area of interest. You can go with a little bit bigger. You can go with a little bit uglier. In a sense, elements are not retaining their aspect ratio. So, what I mean by that? If you got an element that is like this, aspect ratio 1:1, that is the best element you can have. Anything that deviates from that aspect ratio is not good. What I mean by not good, I mean it could be good enough, but ideally you want to aim for something like that. Reason is the way elements are defined mathematically. Remember, like we said, spring element, but what abacus see is k minus k minus kk. Same thing here. We see these elements, but abacus sees that differently, sees that as equations. The way those equations are defined, and they said they are accurate when it's 1:1. Once they start changing or losing the aspect ratio, their accuracy decreases. That may not be significant, but it does decrease. Now, usually aspect ratio changes as you start loading. Yeah? If I was to load that single element, it will end up being like this. And that is basically what elements do. It's their job to do that. But they eventually, they said, their accuracy decreases. And it's okay because they are deforming. Now, if you got element like this, that starts off being ugly and not 1:1. And when it starts deforming, obviously accuracy is not going to be as great. So you have to be mindful of those things. When we talked about regions of interest, this bit here is also so-called region of interest because that's basically where the load is applied. Right? So you want to make sure that you got enough elements in connectivity so it's transferred over here. Yeah? So let us go and do some of those changes and improve potentially mesh. So one first thing would be to reduce element size. And let's see what we have there. Okay, a little bit better, yeah. Then we may go and do edge seeding, for example, here around. Oops. And I say, well, how many you want? Well, we had, let's say, at least 10. I don't know if I changed anything, improved anything, but that's okay. Maybe this edge. By size, maybe we go 10. Okay, it doesn't really matter, but it illustrates the point. 70 to 80% of your time is spent in here, figuring out mesh. So that's basically what most of time engineers spend on when it comes to preparing models. Defining boundary conditions and applying them is not as time consuming. Everything else is. Critical part with the boundary conditions is you can go wrong. You can put completely wrong boundary conditions that do not reflect reality. This is a bit sort of a process that takes time because you have to try this, try that, what's happening there. But eventually you would develop a technique, a way of looking in these situations, it's good to do this, and so on and so on. Let's go ahead with this. So that defines shape, that defines size. Now we need to define type. What type of 2D elements we are using. And we go that by clicking here, assign element type. So we got options. Is going to be plane stress or plane strain. We agree on plane stress. Now, what are the other things that we can make decision? Whether it's linear, whether it's quadratic, whether it's full integration, or whether it's a reduced integration, or it is incompatible mode. So what would you go with? If we take this to be our element, okay? So remember, at the corners, we have nodes. And inside, we have integration points. If we have, this is full integration element. If we have reduced integration, that number reduces by 1 in each direction. So goes through in Y as a full integration, 1 chops off in that direction, 1 chops in that direction. Basically, you end up having 1 in the middle. So that is full, and this is reduced. So that's by checking that box in or out. We choose how many integration points we have. What I've shown here is linear element. What it means that edge is linear. It cannot curve. Yeah? If we had additional, it's called internal node. D and D. What will happen because of that? Your edge, if we move that point, for example, over here, you would be able to have a curvature that goes like that. Then, if you got that scenario, it's called quadratic. Remember, like in a linear and quadratic equation, like a quadratic equation is a curvature. Yeah? Linear is a line. So, that's basically what happens, and that's what we are choosing by having those. Each of those options come at a price. So there are pros and cons of each. Yeah? So, again, I'm assuming that you watch those videos and you know this stuff. So what is the issue of linear element with reduced integration? What is the issue with it? If you got your structure that's under bending, and you got a bending load, and you are using linear reduced integration. So let's maybe start with what is good about it. So what is pro? So linear reduced integration. What's so good about it? Why are we using it?
Lesser processing.
Exactly, fast. Yeah? Much quicker, you can bang, 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 get results quick. So remember those matrices that we talked about, yeah? He's got one integration point, basically where the stresses are calculated, compared to 4. So at least, but it's more than that, at least that one day with reduced integration is 4 times quicker. So that's good. What's bad about it?
Less realistic.
Less realistic. Let me write it down, let me start unpacking. What do you mean by that? Let's start with you because you suggested.
Like some, maybe there's like crumpling on that element, it doesn't show, I think.
Chorus, at least you're going in that direction. What did everyone else think? What is the problem with this? With linear reduced integration, especially on the bending? Have you heard of hourglassing? No? Watch those videos. What happens is that if you go with the reduced integration, so the way usually it's calculated, Abacus looks for changes in shape of those elements. So what could easily happen with these? Because these edges, if you are, let's say if you are bending this element, yeah? So if you put a load there, yeah? What will happen? What will happen, let's say, if you got a structure like this? And you bend it. How would that deform? Yeah. The structure would probably do something like that. Yeah? Makes sense. Now, what happens there is that at that point where the load is applied, you got more vertical deflection. You got more of that deflection than is here, for example. Yeah? So essentially your structure has got a bit of a curvature. Same at the bottom. It looks like that. Yeah? Now, imagine this element here. And we said it is a linear element. So this one here, this edge, both of these edges, that edge and that edge, it cannot curve. Yeah? So, if you want to capture a situation like this, what you will observe is that this side just gets a little bit longer and this side gets a little bit shorter. Yeah? That's basically what happens. So that's how that element deforms. Because edges, sides, they cannot curve. What then happens is that due to that deformation, because you got only one point at which stresses and strains are calculated, this element is not able to pick up this deformation. So although element deforms, because you got too few integration points, it's not possible for this element to identify deformation. And you got situation of so-called hourglass. And you observe that by having elements deforming like this, like hourglass, because you got it's sort of cascades. So basically that's where the term comes from, hourglass. What it means, what essentially says is that there's no deformation. Something called strain energy is zero. And in reality should not be. So if you are using those, that is a problem. Yeah? So what is the alternative? Alternative is to go with what? Full integration. Again, those come with pros and cons. It's much more expensive. That's one thing. It potentially solves that problem of hourglassing, but creates another problem. Another problem is called shear locking. So if you go with the full integration, so linear, full, you got shear locking. What happens, just a bit more theory, but again, you're watching the video, is elements are stiffer than they should be. Yeah? So results that these elements report, they tell you the structure is stiffer than it is, than reality shows. For example, in reality, if I put 1 Newton on this book, it will bend. But if you run an analysis, Abacus would say, if you put a 1 Newton, it's going to stay like this and would not change. It says it's much stiffer than it should be. So that's a problem with these elements. So generally, they tend to overestimate performance of your structure. Yeah? So what are the other options that we can go? We can go quadratic. Quadratic solves those problems. So quadratic are more expensive because why? You got originally 1, 2, 3, 4 nodes, but now because your edges are able to curve, you'll have those additional nodes in there. So all of a sudden, number of nodes bend goes up. So if you use quadratic elements, very quickly you will reach your license limitations. So if you use, let's say, what is that for? So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There'll be 10 nodes for those 4 elements, but if you switch it to quadratic, all of a sudden that goes up by that many extra. So you will exhaust license. That's basically where the cost is. Again, same story, because you have integration points there, they will take much longer to compute. So quadratic elements, although they are accurate and more accurate, they are more expensive. So the good compromise between the two would be to go quadratic but reduced integration. So it will be still more expensive, but not as much. Now, these issues become relevant if you are dealing with bending. If you do not have bending, if your structure does not bend, you don't have issues of shear locking, you don't have issues of hourglass. It's only because of bending nature of the bending, how that puts deformation on your elements, that you have these issues. And that's something that you need to identify and report in your exam. If you are given problems like this, I want you to know, I want you to report, to tell me what size you use, and also what element type you use and why. If you submit your work and you use linear reduced integration, and you haven't explained why that is a good option, and you said completely ignore the fact that there will be chance of hourglassing, or even if hourglassing is visible, then obviously you don't know what is going on, and it would not be complete ends. Yeah? So element types, when it comes to these sort of 2D solids, is important.
How we can identify now? How we can identify?
Let me try to replicate that. So if I go back to and delete this. Said we're going to have. So what element types cause hourglassing? Linear reduced integration. Yeah. Hopefully I'm able to. Enough. I'll bring you one. So. Okay, this is a perfect example. You can see here the shape of hourglassing formula. Yeah, that shape here. See, it's here, gets propagated everywhere else. So this is evidence of hourglassing happening. Yeah? So if, yes, this is extreme case, but very often could be visible. Another way to sort of observe this is to track how much of strain energy we have, or so-called virtual strain energy. So when you go and assign element type, abacus, so hourglass control, hourglassing stiffness and so on. Abacus deals with this. It's a fully recognized limitation of those elements, and there are ways to deal with it. So what happens in elements that are like this, that they form like that? Elements have zero strain energy. So what will be the best way to if you start off like this and you turn out to be like that, and you have one integration point that is here. So what happens? It checks for deformation of those sort of lines that are there, distances. So see, before and after, that line is the same. Before and after, that line is the same. Therefore, abacus goes, it says strain energy equals to 0. Although element has deformed, it deformed because it can't do curvature. If you had option to deform to curve, it probably look something like that. But because it's linear, I cannot do that. So abacus will detect 0 strain energy. So what it does is as artificially abacus adds strain energy to sort of rectify that problem. And at the end, you, depending on how much of that artificial additional strain energy is added, you can detect how much of hourglassing is happening. Okay. So, do you want to finish this up yourselves? Yeah? So remember what I did here with the load? I put a point load. I want you to try and use other approach. So variations to this. Solve the size of the bolts. Use alternative load application. Let's do that. Probably we can finish this in the next 15 minutes. And then we got one more example and we are done for today.
It is another software like
That's why 我那时候软件是这样，我花整天呢，用几年过那么多我软件我那整天的地方做我们盯什么？你给我一个 semester，一个 semester 不够，还是要2个 semester。 3D 的东西，就是这个，
像我们在做，
就是算是不一样，你跟你说是 3D 手，它更准。这种说我学的。
你这个猫呢？
什么就算了，哎，挺好的。说到想不到，想不跳，不太分。
哇，我觉得我。I can say no use one. You just remember what you in our class you just select linear, then the reduced integration just remove. That one render it. 我是觉得在assignment你要 explain 为什么你要这个。如果想说你 just 选 linear。
But why can we indicate by
如果我们要去ask， 法律方面问嘛，不要过去。
Because it's two-dimensional, yeah, you can't see it.
你说安迪吗？有那么了。
Because it's two-dimensional structure, you can fit it from mathematical inside.
我说人如果人家上面有一个很广，
因为没出来，
You need to assign it, yes. Have you made it?
好，我看。
多少岁到？
So anything wrong or is it?
Yeah, anything wrong. So I never do the.
Yeah, that's the problem.
So I have to.
it's just that because this one is very fine that's why you never end up like
因为我没有 update 掉的话，这个 usually 要 update 掉。
Usually starting.
对啊，所以我已经有一个 linear， then just update 一个。法人努力上面。
I need to know the process.
Yeah, put it this way, like if you have 20 elements on there, where would you put
I
it?
think we just
You
need
know, you said because this is my region of interest, I would put 15 here and 5 everywhere else.
Right.
That's what it is.
That's what I'm going to.
So the reaction force will be the boat load, is it?
Yeah, roughly.
Only for initial loads and loads DC should How do you go back to the nutrition as well? Okay, I know how you work your off the table. So you see this one, right? I'll take this one, and then she'll force it. Just get the extra. So she'll take maybe 7 to 8.
When I draw the outset, the part that goes on the shell, I increase the section, why I need to give it as all.
So shell in a part creation is sort of a CAD feature, but in property it deals with whether it's solid or shell as abacus features. So they are not the same. Although they are all the same, that's what confuses us. So this is solid, but this is shell, as in behavior. But when you are sketching it, the question is whether you're capturing lines or you're capturing what's enclosed by those lines. So two different concepts, although they're all the same. It's confusing for everyone pretty much once they start dealing with it.
So you create the mesh in like a box where you want to delete it. So you delete it, we delete it.
应该是我们省略到这个马上，这个3D 可能可以。
哦，
天才智。
所以现在这 looks like a kid. Yeah, but then another thing is you want your load, the whole load, so it goes around. So it goes around in circle direction. We didn't do that.
If the book size is not sufficient, recommend standard diameter. Assume. Oh, standard material for both.
Okay. Dia record. Alright.
会想可不可以来今天做完全部做一点先摆进，then 明天我再做。
这边应该也看到。
要不要问他，看他这样会这样？
没有啊，我觉得我本来是这样子。这样他有很多，这样我是觉得不错吧，just 很多就是不好看是不好看的啦，OK 啦，我觉得。
But I find it's okay because like at the places whereby it's of concentration, right, it is concentration. Especially the areas here, right, it is where the stress is concentrated. And if yeah, it's concentrated, then
可是我放这个，我会用全部 aluminium， 我会因为 aluminium 它的 U strength 是最低的，所以如果我们用这个 aluminium， 我们这个 bus 全部都 bus， 因为它的这个elastic 最低，对，它的 U 也最低。所以只要是它这个 model bus 全部 material
因为这个是最 soft 的material。
最 soft 的，这个也是最快最容易搞的，所以这个只是一个 upgrade。所以你这个你拿到 material 来，你拿到什么 material？什么 stress 来？你这个一定就是比较难。如果有可能这个会坏，把这个给我，这个然后有点高。
因为你已经用最 soft 的 material。
对啊。
因为我跟 use this as a justification，你要 try other material。
没有，我们 justification 是讲，OK， 哇，这个本身有这个 material 大小，如果它要 more performance，它可以变成titanium或者可以变成那个比较高贵的但如果它用titanium的话，它还可以在那个表示，就是我不要是那种。I mean in a way 我们就是 in a way 我们没有讲 optimize， 但是 at least 我们。
But the very thing you save money。
Yeah， 肯定是最忙的。但如果要新玩，你要做多一个模的，如果你要做一个 3D 的话，你要 take
没有，其实这个 one cost use the cheapest material。
这个不是最 cheap 的，最 cheap 是 steel。
steel
很重要，没有 steel 很重要 ，steel 一般，这个钢的话是一般。But steel 你还可以再扣这个位置 ，but just that 它的。我不要做，我没有做到去真的去到刚刚好看的那个可以过，因为那个是很耗时间，所以事情不要，我就是非常满意我这个我的一个部分的这个没有，这个你可以放下放什么，这个只是我要。没有 make it clear for me。
I tried downloading entering the desktop, I didn't work.
你要一篮球？
哇，还是一篮球一篮。
I eat breakfast. I eat brunch.
不是不是不是。
Brunch is the first meal after the meal.
啊，不是。
So usually I go back, I will eat very dinner. Just tired, just sleep. 那种，就他们人总说那
you use which one?
I used the desktop.
Yeah, you need to use the base.
Yeah, I did.
The previous one. But now I doing the new one. Then I will ask you all to open using 2022. If you use 2022 to open, right, your learning edition will open.
No idea why this isn't working.
maybe because you
It didn't work.
Because they will have a pop-up like ask you like permit use or something, not access of the web. Or you got the C3 workshop, it works great. C3 works great.
You try open in Tigo mode or something like that. Wow, shit. Second question.
I think 这个它有在那个 video 做过。
Video?
你把那个 video 的。没有，这个不是，这个是要因为你那个 thickness 你跟我
为什么？哦，uniform 诶。
没有，就有10个，把你不用，你就 set 2个。
What is the same throughout?
No, but then I think Shao is technically 3D space is it not?
What's the force?
Force is the top
fly
plane.
over the top.
Square.
I think it's shell, then you can choose for shell.
I think like the 4 point can put the force.
But this one is uniformly, so you can do this side. You can just do this portion, then you just do as a plate, right? You draw this shape. Then because it's uniformly across, so you can just see from 2D.
Oh, yeah.
Because you put at the same place, right? Just assume that.
I think those are 25 moves, 25 meters.
Yeah.
因为我们一直做，我们不是做那个电影系统，我们的那个 OS3 3年，我们什么地方或者我们做跟做必须得对应。
对，你去 setting， 它有一个 setting 可以选 pressure， 所以when你选 pressure 的时候，跟你 click 进去，它会highlight 整个 setting， 它会 highlight 把它。
对，就我们只是待在上面那个。
Yeah。快多一些。太烧了，搞定了这个地方。所以应该是趋低手。应该是2D的，我觉得。
那我要放2D了。
Okay, so if we move to last question or last exercise for today, we've got this problem. My first question for you is, if this is our problem in 3D, is this equivalent to this 2D solid model? Like, okay. Yes or no? Someone says yes, someone says no. Who says yes? Let's see who says no. Why no? Correct answer is no. So whoever said no guessed right. Why? Question is why? Why they are not equivalent?
The 4-pin joint is up there.
Boundary condition.
Exactly. What this assumes that you have a boundary condition along the edge at every location. All those ones. Because remember what we said, when we do 2D solid, we model front face, and whatever we model there, we assume continues in depth. But what we have here is that we have boundary conditions applied at the corners only. So because of that, because we know the structure could sag, structure could deform between these sort of points like that, we can't use 2D solid. So it has to be 3D. Next question is it going to be 3D solid or 3D shell? 3D shell. Why? Because it's got one dimension much smaller than the other two. Yeah? And loads are perpendicular to it. Remember that story that I showed you with the sheet last time? That shells, they like to be loaded like this, to do this. That's their job. They love doing that. Yeah? So, how would you then go and model this? So normally, there are other ways, but normally what we model is mid-surface. So we will go and model surface that goes like this. And everything else. And then if we, let's say if we take this bit out, let's zoom into there, you will have thickness like that, and you got your mid-surface. Now, surface doesn't have thickness, yeah? So mathematically, we would assign half of the thickness to this, to that side, and half of a thickness to that side. Yeah? And that's called mid-surface. It's in middle surface, yeah? And that continues throughout. Yeah? Conceptually, does this make sense? Yeah? So, we are basically saved. So we don't need to model this in 3D. Yeah? It's a shell. What do you think? How can we change this structure that we said it is no longer possible to model it as a shell? What change we should do to this structure? So we said we are forced to model it as 3D, we can't use a shell.
If that thing is not hollow in the middle, if it's a block.
Well, surface could be like a top one, let's say. So it fixes the problem. But it's on the right path, yeah? What else? It's related to this. If you have structure that is like that, yeah? And then you put mid-surface through it. See what happens? Thickness changes. So shells cannot do variable thickness. So if you've got a structure that's profile of it that changes, for example, like here was 5 millimeters and here was 15, and it was like going on a slope. So if it was going like this, we would not be able to model it as a shell. This would not work. Yeah? Also, if you had any hollow bits in this direction, because along the all lines, like if it's hollow from the top, it's fine. But if it's hollow that direction, would be problematic. Like if you had somewhere inside here, like a pocket that goes like that, it will be trickier. Yeah. I mean, in this case, it would work. But let's say if it was like this, you've got a window there, and it goes like that. So rather than being seat all the way through from the top. So those things will prevent you from using shell, and then you have to go through this solid, and it's a pain. Yeah. Okay. What is the other thing that we can do here to simplify? Have you learned about symmetry? Yeah? I think you did. In the very first example, when you dealt with the 2D solid, you had example of symmetrical structure. Remember that? Remember that problem that we have like this? Yeah? But rather modeling the whole thing, we said how about we put a boundary condition there, and we don't model that bit there. This was a symmetry boundary condition. Remember that? Could we use symmetry there? Yeah, we could. So we could split it here. And just model one half. That would save us nodes, computation, and so on. So let us do that in Abacus.
The section is symmetric, but apply load is not symmetric, cannot use that.
If the load is well, yeah. A comment here which makes lots of sense. To use symmetry, we have to have three things symmetric: geometry, load, and a boundary condition. Boundary conditions. Only if you have all three of them symmetric, then you can use symmetry. In this case, we do have that. You got the same boundary condition, we got the same load, symmetric load, we got symmetric geometry, so it's full symmetry there. Okay, so major difference. So we go 3D modeling space, deformable. Now, had I gone with solid, I will do 3D solid structure. But that's not what we are modeling. We are modeling 3D shell. Now, ask us here, how are we going to model this? Plane means whatever I sketch, thickness gets sort of attached to it. So basically I'm doing planar view. Extrusion is if I do lines, those lines will be extruded into plane. So, and revolution and so on. So extrusion makes sense to me, yeah? Because I'm modeling this blue. So basically I'm modeling those 1, 2, 3, 4, 5 lines, which I'll extrude into this direction. I'll have surface. Okay, now we're going to achieve. So what's 200, 200. Okay, so what's wrong with this picture? It doesn't capture the mid-surface, does it?
The minus thickness.
So, this bit here, the black edge here is 200. What is the blue length?
193, 197.
197. What is the blue length here? It's 150 minus 12. Yeah? Half of thickness factor. So minus 6. Yeah. Half of thickness there, half of thickness there, minus 6. It's 144. 150, this one here, 197. So we got, this one here is different. Again, it was 250 minus 6. Yeah? 244. Okay, so I'm done with the profile sketch. It asks how much to extrude and what is the depth, 250. Ta-da! Done. Yeah? So that's geometry part done. Okay, what does it say? It's steel again. Okay, now again, a different thing from what we've done before. So when it comes to section, when you create section, in category here, we used to click solid. We had to beam and trusses, we had solid for 2D solid and 3D solid. Now we have to use 3D shell. So basically, shell as a section is different from shell as a sketching feature. Yeah? So we have to use shell homogeneous. Remember, I said in your 2D solid, we used solid as a category, as a section. But here has to be shell. You go continue, and here asked us what is going on. He said, well, we have not modeled physically thickness. We said this is a surface, which is a feature that doesn't have a thickness. So in here, in section, we would assign thickness. We would say 6 millimeters. Similar what we did with plane stress, probably. We didn't physically model thickness, but we assigned thickness through section. Yeah? Okay. Now we have geometry, we've got section, we need to assign it. And we are assigning it to all. And this is basically where we are saying shell offset. And it says mid-surface. So we've modeled mid-surface and we are doing that. We are saying half of the thickness will come on one side, half of the thickness will come to the other side. Abacus allows you to have other options. Yeah? So you got top surface, bottom surface, or specify. What it means? It means that we could have done this. We could have modeled this edge here only. So the bottom surface and do the same job. Rather than going through that trouble of finding middle surface, we could have modeled the bottom edge or top edge and then go here and choose where thickness will be assigned. Is it going to be assigned to the top or to the bottom? Yeah? So in our case, we had mid-surface and we okay. And then we go assembly, create, bring that in. Okay. Now, one thing that you may do if you go view, assembly display options, you can render shell thickness. You can actually see it. So we've got a scale factor of 1, but I can make it like 3. Sorry. So everything is 3 times thicker than it is. Yeah? So you can see what's happening there. Yeah? If let's make it 5 so we can see what's happening there. Yeah? So see it's a middle. Now, if I was to go to that property, could I see it here? I can see it here as well. No, good. So if I went to that property and change it and said, look, let me choose that as being top surface. So we pick top, yeah? Okay, dismiss. We go into our assembly and see what's happening there. So thickness gets assigned on top of what we sketched. Yeah? Does that make sense?
Yes.
Yeah. Good. Now let me go back and change this.
你 zoom out 你有一个 view， 因为那次你 zoom out， 常分你 zoom out， 跟你这个 view 按然后会自己你去 view， 你去 toolbar， 没有under views， 那你 just click 其中一句吧，那个出发出来的其中一句。
Now, another thing to be really mindful of is that when we talked about 2D space, we had X, Y, and rotation about Z. So basically, in 2 dimensions, all you could do is go up or down, go left or right, and rotate on this plane, yeah? So without leaving this plane, without leaving this screen, I can do this, I can do that, and I can do that, yeah? So those are degrees of freedom. When we are dealing with the 3D space, we can go translation in X, Y, and Z, and rotation about each of those axes. So all of a sudden, every point is got 6 degrees of freedom. Yeah? So your boundary conditions, again, this is my preference. I would lock all of them in initial step, then I will go to active step, this analysis step, and make it what it needs to be. So what we have here is a pin. What is 3D pin? What is pin to start with? When you said pin is as a boundary condition, what is it?
Rotation is free.
Translation is locked, but rotation is free. Yeah? So it means my 3D pin will free up rotations. Yeah? Okay. Now let's do a twist. I love doing these twists. Let us say we have a roller here.
How do you set the pressure? Only the top. Only the top.
What does roller mean?
Translation in x-axis.
In X?
Y is equal.
So in this 2D space, yes. So what is happening in 3D space?
Y and Z.
Y and Z is locked. So let's define it so we talk about same Y and Z, yeah? So we got X, we got Y, and we got Z. So is that the same as what we got there? So which of those are locked? And which are free?
Negative down, negative Y.
What's roller stopping us to do?
Up and down, up and down.
To lift off.
Y is locked.
So it's only one that is locked.
So X and Z is free.
Yeah. So it's basically, it's a free to run, basically to do this. But I can't do this. I can sort of roll, like, you know, when you've got a roller as well, you've got a roller blades, you know, I mean, you can fly as well, but like, you know, most of the time you're just rolling, yeah? So had it been roller, you only lock one, which is vertical. It doesn't have to be, it's not a vertical always, it's always perpendicular. Remember that crane stuff that we did yesterday.
Just
When we had
why
that
don't you?
structure that was, carrying the box and so on, and we had roller there and a pin there as well. Yeah.
Use one for all four.
So we're stopping lift off in that direction.
One for all.
So it's not always vertical direction. It's basically where we do not want that lift off to happen. Yeah.
So, but this boundary condition means it's at the midpoint, right? Do you need to, does that matter? Because now your points are at the midsection.
Well, yes. So what we are saying, we are representing structure with that mid surface, and we are happy with that representation. Yeah. Load. Yeah. So what we have here is pressure. And pressure is applied on surface. And see, surface is got two sides. Yeah? Because this book is thin, but it's got thickness. Yeah? So it's easy to say, okay, is it this purple or this white side? Yeah? But when you got something that doesn't have thickness, when you select that, you don't know which side you are selecting. A surface does have side. So that's basically what's telling us here. Where is that side that you want your pressure on? Is it going to be this purple side or the bottom, which is brown? So you have to choose. Yeah, for us, we want to have purple. Yeah, and says how much pressure, whatever. Okay, 70 kilopascals. What is that? Remember our lengths. Our lengths are in millimeters. So 70 kilopascals, how many megapascals is that?
0.4.
Or no. 700 kilopascals is what? How many kilopascals in 1 megapascal? 1,000. And we only got 70. So it's going to be 0.07. Okay, there you go.
So we need to
Mesh.
What material different?
I think 一个是上一个下。
Okay, works out well. If you want to have more control, you will click on Assign Mesh Control,
I want below.
assign everything, and you said, I want to have a quad, I want to be structured. More or less, you'll end up with the same mesh, but this is you controlling it. So Abacus was smart enough to recognize what's going on there and gave you this.
Oh, the brown one is below, the one on top. Very proper, yeah. See the packet purple. No.
Here element type I can leave it linear. Here element type I can leave it linear.
没有，我没有有点。
Okay. Is that what we are expecting to see? Yes, we are. So structure basically deforms the way we want, the way we are expecting it to deform. Yeah? Yes. Which one? Load, okay, yeah. So on the load, so boundary conditions. So in the boundary conditions, we said it's a pin, so we are not allowing it to translate at all. So that's the boundary condition. And then if you go to load, we go for pressure. So you would go pressure, and then you specify how much of pressure you want. And it's uniform pressure rather than anything else. Yeah. And that's it. Now, to solve this, it took on my computer 0.1 second. Yeah? So, and to model it was like what? 10 minutes? Now, how about you go and model this as a 3D solid? And see how long it will take to finish modeling and how long it will take to compute, to solve. And that's going to give you a bit of experience how to go about 3D solid. I mean, you saw 3D shell is very easy, it's not that complicated. You have to just recognize whether we can model it as a shell or not.
It's quite easier lah. Even circle that one for full very troublesome.
What is 0.070?
Megapascal, because we are doing in mm. The pressure is supposed to be megapascal.
Megapascal shouldn't need Newton. It should be 70,000.
So your 20 kilopascal. So kilo is smaller.
70 Newton.
Kilopascal.
No, it's kilonewton. Kilopascal.
Yeah.
Oh,
So you need to minus. So you need to times 3. Kilo 3 bar. 70 times 3. Then divided by mega.
Kilo to mega. Kilo is E3, right? Mega is E6, so you need to divide by 1,000.
Yeah,
Oh, okay. I thought it's kilonewton.
Pascal you can see what?
No, Pascal is Newton per minute. Newton per
So when you
minute.
say they give Newton, then how you convert to Pascal?
Newton to Pascal. You need to divide Newton to
Pascal is
force over area. Force over area. Newton per meter.
yeah,
Force is
So it means 1000 Pascal equals to 1000 Newton.
1,000 Pascal. If area is 1 meter cube, then it's 1,000.
Right. So they said in the question they give you like 70 Newton.
Yeah, then
you need to know the area what.
we need to divide.
All the question, some question they give Newton. Yeah, I never do the I just say
Actually easy. If Newton is usually is point.
point one. Point one.
Yeah.
Point one
Unless you do the point load thing instead of doing the
they actually need to cancel to remove the wall space.
But for me, I never remove just see the size. Even with the point load, right, it's lower than our use just just fuck it. No lah.
Wow, shit, all this stuff.
他是讲1 second 很轻易。
Maybe 0.1 second to
那什么电脑？
没有，听证是他自己的 ，maybe 不是用，maybe 不是用学校的。
There'll be some variations for thickness. You have 3D solid will give you more detail. So you may realize that, for example, due to boundary condition, we'll have a region here that is highly stressed. Shell that may not pick up that much. But roughly, generally, you have it.
Ba sao vậy? Show sao thì 야 컴퓨터 있네. 컴퓨터요. 와. 야 맞지? 좀 많이. 왜 그래요?
No, just now your roller you your boundary condition. You need it. This one is not good. Because this one, actually the question never say is then it's just assume
But then it's just it's only one. The rest is
yeah. No, roller is everything. Pin is everything.
everything locked.
Yeah, everything.
If you want to remove this, how do you remove it?
Usually you need to undeform the thing.
Okay, so was this helpful, these 3 days? Yeah, that's good. Now, as you know, RMIT is no longer running this program here. So you better pass this, otherwise we'll have to come back for 1 or 2 students, so I don't want to do that. So study and pass, and yeah, hopefully we can see each other again. Well, you know, I can't do those shifty ones. No. So hopefully I can see you all again at graduation if you come to Melbourne. I had fun. Sorry for coming late yesterday. It was just unexpected. If you got any other questions about anything, please shoot. Now it's time to do that. Well, we got about 10 minutes, so we can finish a little bit early today. It's Saturday, you got to do something else more important than this, I assume. Okay, now, last question. Do you have any questions? Extension, I'll sort it out. Yes, I'll sort it out. 1st November, I'll do that. I think so. It should be a problem. Yes. Okay, well, let me sort of go back with the answer. So what I said to Kaplan, I said, I don't really care what students bring in. What they need access to internet, they need access to abacus. And then Kaplan, they got their own rules. So they may say, look, you know, we don't allow students to bring laptops, but they must do this. So that's something that Kaplan will communicate to you. To me, it doesn't really matter. As I said, originally the way we ran this, like we could have done this from home. Doesn't really matter. But Kaplan wants you to come back here to classroom and then use it. Now they got other rules. Said, okay, should they bring laptops? Should they bring this? Should they do that? And so on. So that is something that will be communicated to you by Kaplan. As far as I'm concerned, you know, you don't need to even come to do it, but you can do it from the home. Okay? So that's something that you know you'll have more information from coming from Kaplan.
Is that for home? Is that for home easier? No. I cannot even find my boundary condition property 很像。Can you explain the boundary condition again? Can you explain the boundary? So the boundary is only x, only the y-axis only, right? Or is it
So this one here is pin. Yeah? So when you're pinning something, you don't want it to move anywhere. No translation at all. Yeah? When it's rolling on a surface. Yeah?
Yeah, got it.
So it can't lift off.
Okay, like that. So how do you see it?
So basically, design stress, right? Our stress, our body stress, cannot be more than 160 megahertz. These are all.
So it is 1 point.
So 1.6. Then deflection right, which is here. This one cannot be more than.
So the red one has a higher rate of reflection, the blue one is pretty less.
So these are all within our parameters. So based on this, right, our deflection cannot exceed 0.15. So this is 0.11, which is nearly limit. So, yeah, so this one got more deflection than this. Because this one is our model 1, this one is model 2. So what I do to this is I reduce the thickness to bring it more to the limit. This one already passed.
Okay, so all the best. Good luck on the exam, and that's it. See you at the graduation ceremony.
Very small bit. So another thing is this one. How do we get the UI from the rest of the thing? So you can see this is This is kg.
Based on your density, so density you put kg for every kg lah.
This is okay. Model 1 is we just get this figure lah. Because as of now, what you need we also don't care because you just need to know the percentage. So this is 1.5. Yeah, this is 1.11. So you can see there's a reduced rate. Yeah. So as long as it's more than 12%, it's fine.
Just screenshot.
Yeah. But this one cannot really screenshot. This one like where are we? Yeah, I mean like this whole batch bunch of so now I finished with so now only have so for actually for this one, this is virtual desktop. You need to open the yeah, but this is 2022. You cannot access my file because they will say the version is
Okay, let's say I had 2022, how would I access the file?
it's the same. You just file open. Then you must find the CAE file.
Under where?
Where do you save it?
I save it on my desktop.
Oh, then you go desktop.
Upload to the cloud.
So this is virtual desktop. So you go home.
So this is the form of the page drive.
This is
So you want feature now is your own drive. Which one is your best now? Okay, I mean desktop, right? Because the audio will hit the desktop because of the file. Due to like
No, I mean as in my computer desktop.
no, you can access.
Oh, so I have to transfer it here. How do I transfer it here?
You need to send email to yourself.
Oh, I then open and then save it as.
So my book.
Send my email and then
So this desktop right is like somewhere in America they are server.
Okay.
So you need to send to yourself, then you need to access your email in this desktop.
and then save it to that
Yeah,
desktop.
but the problem is you cannot send email to yourself because the system will recognize this file as virus because I know some file format they will recognize it. So what I recommend is you log in your WhatsApp.
Okay.
Yeah,
Into
in
this
this
desktop.
use the web WhatsApp, then you send to yourself.
I see. Okay, I get it. Okay.
Anyway,
You will send us a different file.